Welcome back to ECE 441A, 541A. We will begin today with a quiz, just to get our adrenaline going. That's our first goal, but as way of announcements, homework number 4 should be available on D2L, and that's due on Wednesday. Exam 2 is actually 2 weeks from today, on the 24th, and soon thereafter is homecoming weekend, and that Friday before the homecoming game is engineers breakfast. We've been encouraged to not have class, especially if the class has a lot of seniors, and so we will not have this class on that morning, which is the 7th of November, and I'll be taking attendance at the breakfast. That will be your quiz to see how much of your breakfast you can hold down with me taking attendance. Today what I want to do is get into Chapter 5, which is to discuss design specifications. How can we now specify where in the complex S-plane we want the poles to live? And here we're talking about the dominant poles. And hopefully it will become clear as we move through the material or this class what we mean by the dominant poles. But we're looking for the location of two poles that are associated with a quadratic set of roots in the denominator, and we want to know where those located relative to certain transient response behaviors. To get you thinking in that mode, let's now do a match quiz. So what I want you to do, here are the rules for the quiz. Individually, you'll look at these two pictures. One picture will be a set of the poles, two sets of poles, and one picture will be two transient responses, and I'm simply wanting you to match the poles with the time response. You'll look at that individually, not for very long, 30 seconds maybe, then get with a neighbor and convince that neighbor why your answer is correct, which pair that you've selected. Now, if you're playing along at home, you can do this with your image in the mirror. So that's what I'm meaning by or the mirror, but convince your neighbor. Your neighbor might be your mirror if you're doing this at home. All right, there's 3 of these pieces or questions to the quiz. Can you see that? Is it clear? So what I have is I have 2 sets of poles. I have a set B, which are in blue. This is one system, and the other system are these green poles. So those are 2 different systems. This isn't one system with 4 poles. It's 2 second-order systems. The blue poles correspond with B. The green poles correspond with A. And I want you to tell me, do the A poles go with trajectory 1, or do they go with trajectory 2? So you really just have 2 choices. A goes with 1, or A goes with 2. Is it clear what I'm wanting you to do? So match up the poles with the time response. A with 1 or A with 2, and that will obviously give you the B with the appropriate match pairing. Is everybody clear? Go. Is everybody already matched? If you have matched, get with a neighbor and convince your neighbor. Maybe you just do one neighbor this time and we'll switch it around. We're going to have 3 of these. But now try to convince your neighbor which set of poles goes with which response. Is that clear? You don't have to move too far, but now just meet with a neighbor and we're going to ask for your answer. Boy, I hear a lot of discussion. So the colors on the two diagrams may not be consistent. So you may not, A2 may not be what matches it may be. Does everybody have an answer? So on the right, the blue poles are B, and the green, so the coding is blue is B in that one, and A is green. And on the left, trajectory 1 is blue, and trajectory or response 2 is the green one. Is that clear? It is a little maybe confusing initially, but hopefully you get the idea. All right, now show of hands. Let me see if I can go back. Maybe I should have somebody counting for me. How many people or teams picked pair I? Do you remember what pair I was? It was the one on the left. It was A1B2. So that was I, and 2, response 2 is A2B1. All right, how many were, I shouldn't have you looking around. I should have you just show me a 1. Show me a 1. Anybody? Show of hands. All right, how many were going with 2? Wow, I don't even want to count. All right, we'll just say a lot. And you'll be able to read that since it's in highlight. Sorry about that. Let's go back. Question 2. Now, the A pair is blue. I don't even know if it was before, but it is this time. That's one system. And here is the other system. B is in green. And I've tried to, there's your S-plane axes. Although the vertical line is actually straight, it's not curved. But now, which response goes with which set of poles? You can go ahead and convince your neighbor if you haven't already started. Does everybody have an answer? Or was your neighbor not wanting to be convinced? All right, let me make sure I have something that I can write properly with. Question 2, how many were I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Roughly 12. How many were 2? 1. Maybe. Maybe I missed some. All right, question 3. A is blue now, and that's this set. And B is this set. And match that with 1 or 2. Now I don't feel so odd when I start doing this. I see some hands doing. Did we get an answer? Are we brave enough to respond? I. 1, 2, couple. Whoops. 2. Okay, 14 and 13. We didn't vote. Somebody didn't go to the polls. No. You can still register to vote in this class, although that's closed now in the county. You can't register for the upcoming vote anymore, I don't believe. I think you missed your chance, but we'll allow voting here. So how did you go about classifying or categorizing the polls? The angle, what angle? Okay, the real and the, okay, I'm going to be starting to refer to that as a pizza wedge or as a pie. I'm thinking that you're saying that maybe you were looking at where were those poles relative to this angle theta. Is that what you were saying? Did you classify them any other way? The magnitudes of the real and the imaginary. And in what way were you using that information? Okay, so this distance you were saying something about damping, or how quickly it settled, and you were saying then that the vertical is telling you something about how frequently or what the period was of oscillation. Very good. And what were you guys using this angle for? Overshoot, percent overshoot, okay? And those then are consistent with these response trajectories, aren't they? You might be interested in the settling time, which is which one? The horizontal distance in the left half plane, that's now this damping. The percent overshoot is our angle, correct? So this is now the angle theta. And then we will worry about peak time. We won't worry so much about the oscillating frequency, but you can also do the frequency of oscillation. And that's this or maybe I should say imaginary component, right? So now what we want to do is figure out how do we sketch these angles and distance into the left half plane and height or distance away from the real line. How do we sketch those if our boss tells us I need a settling time of 2 seconds? I need a settling time of 3 milliseconds. I need a percent overshoot less than 10%. I need a peak time. I need you to get there quickly. I need a peak time of 1 millisecond. How do those now translate into regions in the complex plane? You now have some feel for what those are doing based on your responses to the quiz. So now let's look at how we can formulate these specifications in the form of locations in the S-plane for our dominant poles. To do that, we're going to actually look at, I guess I slid too far ahead, we are going to base our design specs on a pure two-pole system. No zeros, just two complex poles. And the reason that we are doing that is because a lot of higher order systems actually behave just like a two-pole system. You might have a fifth order system, but its response might have some overshoot, some ringing, and a settling time, and you go, I just need to get a good feel for what I can do with this fifth order system. Let me approximate it by a second order, and let me play with it as a second order so that I can at least get some feel for what's going on, or maybe determine where I want to relocate the dominant poles in that system. What we will do is then treat all of our system, well, we will focus on our design specs coming from a second order system. And one such example system, let's say, is this K over S plus P. Let's say this is our G of S. And that could actually just be a DC motor, where the output is the angle of the shaft and the input might be a voltage. Here is our reference input, and here is our output. We have then a pole at the origin and a pole at minus P. In the open loop system, we're feeding the output back around that to generate, now what I'm saying is a second order system, a pure second order system. To look at or to see that, all we really need to do is find the closed loop transfer function. What is the closed loop transfer function for this system? What's it the ratio of? Is that what I heard? G over 1 plus GH. And H is 1. It's G over 1 plus G. If we plug that in, get a common denominator, and clean up all of that, we end up with K upstairs, and then we have S times S plus P plus K downstairs. Or in the denominator, so I maybe skipped a few steps in going the G over 1 plus G, but I think you can quickly get there. This now looks like an S squared plus PS plus K. We do not have any polynomial of S in the numerator. That's now a second order denominator. This is what I'm calling our pure two-pole system. So this is now what I will refer to as a pure meaning no zeros, pure two-pole system. I guess if somebody wants to get technical, they'll say, well, you have two zeros at infinity. Yes, we do, but I'm worrying about zeros in the finite S-plane. So we have no finite zeros, and we have two poles. That's what I'm meaning by a pure two-pole system. And that came about by just having a DC motor with a feedback loop around it. What we will want to do is not worry so much about each unique different system. We want to think in general terms. So let's now just talk about a general second order transfer function that's a pure two-pole system parameterized with the notation or the variables that we've been using all along. Using our generalized notation, we can say then that we want a pure two-pole system, T of S, to be our natural frequency squared over S squared plus 2 zeta omega sub n S plus omega sub n squared. Where this zeta is our damping ratio, and you're going to come to know that be very familiar with that, and omega sub n is our natural frequency. What are the poles of that system? And maybe you don't see those right now immediately, but let's just derive those. What do we know? We know some of our algebra. We know the quadratic formula. And that's just a second order denominator. We can apply the quadratic formula to find our roots. We have normalized it to be monic. So our A coefficient is 1. If we consider this our B coefficient and this is our C coefficient in our quadratic formula, then we have what for roots? We have minus b, which is minus 2 zeta omega sub n, plus or minus the square root of b squared, 4 zeta squared omega sub n squared, minus 4 times a, which was 1, times c, which is omega sub n squared, 4 omega sub n squared, all over 2a. Is it clear where that came from? That's just the quadratic formula. Let's now divide everything by 2, and there's a 4 hiding underneath that radical. That will cancel, and the 2 out front can cancel, so that we can simplify this a little bit by getting rid of the denominator, and we now have minus zeta omega sub n plus or minus the square root of zeta squared omega sub n squared minus omega sub n squared. We will be focusing on complex poles, which means we will be concerned with the expression under the radical being negative, but we can factor out the omega sub n and slide its omega sub n squared underneath. We can pull that out, and we can now say that we have minus zeta omega sub n plus or minus omega sub n, the square root of zeta squared minus 1. And if we focus on this being complex, then we are wanting zeta, our damping ratio, to live between 0 and 1. And if zeta is less than 1, then that argument underneath the radical is negative, and we get this j coming out front, and we see that the closed loop poles from that generalized notation give us minus zeta omega sub n plus or minus j omega sub n square root of 1 minus zeta squared. So I factored out a minus 1 in the underneath the radical, and then I took the square root of minus 1. That's my j, and I end up with this omega sub n square root of 1 minus zeta squared, and that's really just my damped frequency, my damping frequency. We can now sketch these poles in the complex S-plane, and I'm just going to do that with the upper left quadrant. We have a real part let's say our pole is right there, then it has a real part of minus zeta omega sub n. That distance now is zeta omega sub n or sigma, depending on what notation we might be using. This distance, the imaginary component, we've been calling the damped frequency, omega sub d, but that's just omega sub n square root of 1 minus zeta squared. If you square the real part and square the imaginary part and add them together, you will get the hypotenuse squared, which is this distance that pole is from the origin. This is now our omega sub n. That's a pretty sloppy omega sub n. Let me clean that up. Not that that was very clean. But we can now identify several different additional features to this diagram. This is our imaginary axis, and this is our real axis. Suppose that we vary zeta. We said zeta was living between 0 and 1. Where does that pole move if zeta approaches 0? It goes to the imaginary with no damping. That makes sense, doesn't it? Zeta is our damping ratio. With no damping, that means we are on the imaginary axis. So if we said zeta is getting closer and closer to 0, let's keep omega sub n the same distance. We just rotate. We now just rotate that around, and that will go up, and omega sub d will become omega sub n as zeta is equal to 0. Meaning we now have this arch that's determined by this radius of our natural frequency omega sub n. This point is when zeta is equal to 0. This point would be when zeta is equal to 1, when we have two real equal roots, zeta equal to 1. And now, depending on where we are between 0 and 1, we like to actually maybe denote that by this angle theta. And if somebody says, well, how is theta related to some of this? If you said, well, the cosine of theta from my trigonometry is just going to be the adjacent over the hypotenuse, which is zeta omega sub n over omega sub n. That's zeta, which says that if somebody gives you the damping ratio, you know what the angle is. Theta is now the inverse cosine of zeta. What we want to do is relate all of this to our response. Some key points here would be our peak time. We have our, I don't know where to put this to not be too, we have our steady state value of the output. We also could have a tube, after which our response goes inside that tube and stays or remains in that tube, and this could be our 2% tube, which it got into the tube just then and it celebrated with some music. So once it gets into that tube, it now is considered that distance that it of time, or that length of time to get into that tube. Maybe I put this where I didn't really want it. Let me put y steady state here so that it's this time that it obtains. That's now our settling time t sub s. We also have the overshoot, which is measured between the steady state value of our output and the peak value. So this is our 2% settling time, and this is our peak time. And somebody might actually, you might hear people talk about a rise time, T sub R, which if you have an underdamped system, that might be the time it takes you to get to your final value, your Y steady state, at the first time. If you have an overdamped, you may never get to your steady state, so they may consider the rise time to be 10% and 90% of your final value. What's that distance of time between 10% and 90%? And they might call that the rise time. So the rise time is dependent on your system behavior, whether it's underdamped or overdamped. So we won't play too much with that, but that's then faster or shorter than your peak time in an underdamped case. Let's now relate all of those by looking at the time response. Our time response is, we want to know what's the output doing for this generalized system notation T of S, and the input R of S. Let's go ahead and constrict that or restrict that to be simply the unit step. If you have note 1 of demo 1 memorized, you know that the output y of t is 1 minus 1 over the square root of 1 minus zeta squared, e to the minus zeta omega sub n t, whoops, sine, I didn't have it memorized, did I? Sine of omega sub d, which if we expand it out as omega sub n 1 minus zeta squared t, plus theta. And this could be our sigma. This frequency is our damped frequency, omega sub d. And theta sub d is, in fact, that angle that we identified in our S-plane plot. And you could parameterize that several different ways. If you said, what's the tangent of theta? That's now just the imaginary over the real. But omega sub d is omega sub n square root of 1 minus zeta squared, and sigma is zeta omega sub n. And you might then see theta written as the inverse tangent, doing some canceling of this square root of 1 minus zeta squared over zeta. Those are now the expressions and the formulas that we need to derive these design specifications, these rules of thumb that will guide us in telling us where do we locate our dominant poles in the S-plane. Let's now look at these design specifications. Meaning we're trying to put some hard numbers on what you were doing intuitively to begin the class, matching those responses with pole locations. Let's look at the 2% settling time. Which we'll call capital T sub S. If we look at this response, what impacts its decay? Where is it going to eventually end up, y of t? For a large value of time t, where am I going to eventually end up for y of t? If I let t get large, where am I going to go for y of t? 1. And what's influencing how quickly I get to 1? E to the minus zeta omega sub nt, or e to the minus sigma t. That's what's determining how quickly I settle into that final value. Or you've just told me that the decay envelope is this e to the minus zeta omega sub n t. That influences my decay. Or we could write that as e to the minus sigma t, or in terms of a tau, we now have for time constants e to the minus t over tau. Sigma and tau, the time constant, are reciprocally related, and you may see this, e to the minus t over tau, or e to the minus t over rc. Your time constant tau was rc in that first order circuit. We're now saying then that one time constant tau is 1 over sigma, or that's 1 over zeta omega sub n. And the 2% settling time, T sub S, we will just agree that that's 4 time constants, 4 tau. That's what we agree to play by this semester. We're going to say our settling time, our 2% settling time, to get into that 2% tube is 4 time constants. You could write that as 4 tau. You can now write that as 4 over sigma, or you could write that as 4 over zeta omega sub n, and you know what zeta omega sub n is. That's that distance into the left half plane that you want your dominant poles to exist, or be to the left of. And the reason we use 4 time constants is the following. We have e to the minus zeta omega sub nt, but we said that's the same as e to the minus t over tau. If we let t equal t sub s, which we said is 4 tau, then we have e to the minus 4 tau over tau, which is just e to the minus 4, and you probably have that memorized. What's e to the minus 4? 0.02 approximately, isn't it? It's actually 0.0183, but we are saying that's basically our 2% too. That's where that's coming from. Now for an example. Suppose that somebody says, I want a 2% settling time less than 1 second. that now should start producing an image in your head as far as an S-plane picture. T sub s less than 1 second. Well, we know our settling time is now 4 time constants, or that's 4 over sigma, and we want that to be less than 1. Wow, this is some intense algebra. So now we solve that for sigma, and we see that sigma needs to be bigger than 4. In our S-plane, if somebody says that they have a 2% settling time of less than 1 second, that now tells you that, oh, I can go over here and draw a vertical line, and as long as this distance, sigma, is 4 or more, if my poles are over here, let me put some poles in here, hypothetical, if my poles are right there in this region, then I will satisfy that design specification of having a settling time of 1 second or less. Is that clear? So now you just need to have your dominant poles in that red shaded region, which is now defined by having a sigma value bigger than 4. That's your settling time spec. That now corresponds to a vertical line. What about the peak time? Looking at the y of t expression again, we want to, or we're defining our peak time as that time instant when we first reach our maximum, the first time we reach a maximum. And that occurs when the derivative of y with respect to t is equal to 0 for the first time after t equals 0. And if you go back to this expression, and we've done this, I think, leading into, where was my expression? There it is. Into lab number 1, and all of this revolved around the argument of sine omega sub dt plus theta. And we really needed that argument, sine of omega sub dt, to be 0 the first time after t equals 0. We needed sine omega dt to be 0. The argument then needed to be pi. This is now another way of writing that, as we can expand omega sub d as omega sub n 1 minus zeta squared t. We know that's true when we're at the peak, our peak time. So we now can say that the peak time is just pi over omega sub d. If we plug in t sub p for t, since we know the peak time is when this relationship is true, and solve for t sub p, we get pi over omega sub d. That's our peak time. Or we could say that's pi over omega sub n square root of 1 minus zeta squared. Let's look at an example for this. Suppose somebody says, I want a peak time less than 1 second. Now we know time to peak is equal to pi over omega sub d, and we need that to be less than 1. Again, some heavy algebra says that we need omega sub d to be bigger than pi. And this now tells us where we want to be vertically relative to the real line, the real axis. We now can say if somebody wants a peak time less than 1 second, what picture do you see now in the S-plane? If we say there's omega sub d of pi, so what? What are we wanting to do now? So now we actually want omega sub d to exceed pi, don't we? So we need to be living above pi. We need our imaginary part to be bigger than pi to give us a peak time of 1 second or less. Meaning we are now envisioning a horizontal line, and the region that we want to live in is now above that horizontal line. Or our pole in the upper left is now maybe there. And we haven't said anything about where it is in the real direction. And that's influencing our settling time. But to get a peak time, we need to be big in terms of our, a short peak time requires a tall or a vertical distance for our dominant pole. One more performance spec, the percent overshoot. If we look at y of t at the peak time, that's going to be our y peak. We can call that m sub pt, or that's 1 plus e to the minus, if you evaluate this, zeta pi over the square root of 1 minus zeta squared. And we might even call this m sub p. All we've done is we know what time to peak is. That's pi over omega sub d. We substitute that particular value of t into our y of t expression, and we get this result. 1 plus e to the minus zeta pi over the square root of 1 minus zeta squared. And what was our final value for y of t, the steady state, in that y of t expression? It was 1, wasn't it? So we're eventually going to go to 1. This is telling us how much we overshoot that. That m sub p tells us how much we overshoot where we are eventually going to be living. Our percent overshoot then, which we will call PO, is now m sub p times 100%. Or we could say that PO divided by 100 is equal to this m sub p, which is e to the minus zeta pi over the square root of 1 minus zeta squared. If we solve this, PO over 100, or use that, we maybe say, I want a percent overshoot of 20%. We would put a PO of 20 in for PO, and now we have 20 over 100. That's 0.2. Solve that for zeta. And we have what our zeta is, and zeta gives us our angle. Meaning if we do this now for zeta, this is now the natural log squared of PO over 100 over pi squared plus natural log PO over 100, all square rooted. And that particular relationship between PO, percent overshoot, and zeta is diagrammed in figure 5.8. As a percent overshoot curve, that sort of looks like, here's percent overshoot versus zeta. This now looks like that. Such that if somebody were to say, oh, I want a 10% overshoot, and they read across here, the zeta value is roughly 0.6. If they say, no, I wanted a 5% overshoot, which hardly has any overshoot at all, that's now 0.7. Now, what have we done? We've now translated these percent overshoots. Let's say we had a percent overshoot of 10%. That now translates roughly into a zeta of a 0.6. But what's 0.6? The inverse cosine of 0.6 is 53 degrees. That's how big that pizza wedge is. If we said 5%, zeta now is 0.7. What's theta? Inverse cosine of 0.7. That's the sweet spot. That's a 45 degrees. So this is now a 45-degree angle. If somebody says, I want a percent overshoot of 45%, I'm sorry, a percent overshoot of 5%, now they're talking about an angle of 45 degrees. And they would want their poles to be inside this pizza wedge if they wanted a 5% overshoot or less. You'll get experience with this as we move throughout the semester, but this now characterizes this relationship between, and now you can do the intersection of all three. If you intersect all three of those regions, you can meet the three design specs simultaneously with a pure two-pole system. Enjoy your weekend, and I'll see you Monday.